Look up tonight, somewhere away from the city, and the stars feel close. They feel almost friendly. Pinpoints of light scattered across the dark, twinkling at you through the atmosphere, sitting in the same patterns humans have used to navigate and tell stories for thousands of years. The constellations look the way your grandparents saw them. They look the way your great-great-grandparents saw them. They look the way someone in ancient Egypt saw them. The stars feel close, but they are not. The closest one, the one that isn't our sun, is so far away that even traveling at the fastest speed humans have ever achieved, you would be in the spacecraft for over 6,000 years. 6,000. That's longer than recorded human history. Civilizations would rise and fall around your descendants while they slept their way through the void. And even then, when they finally arrived at our nearest stellar neighbor, they would not have made any meaningful progress through the cosmos. They would still be unimaginably far from anything else. Tonight, we're going to take a slow walk outward. We'll start at our backyard, with a small spacecraft humanity launched almost 50 years ago. And we'll keep going. Past the edge of our solar system, past the nearest stars, past our galaxy, through the local group, through the supercluster, all the way out to the cosmic horizon, the boundary beyond which we can never see and never reach, no matter how long we try. This isn't a video about monsters in the dark. This isn't about black holes ripping you apart or supernovas burning you to ash. The truth is something more austere than that. The truth is that the dark itself is unreachable. The distances are real, and they're not going to get any smaller. The universe was built with walls in it, and every direction you look, those walls are there, closing in. By the end of this journey, the loneliness might sit heavier in your chest than any horror movie ever could. Because horror movies end. The wall doesn't. Get comfortable. Lie back. Close your eyes if you want. Let me show you the size of the room you live in. I want you to think about the night sky for a moment. The stars you see when you look up. Most of them are inside our own galaxy, which means they're a few hundred to a few thousand light years away. The brightest ones are the closest ones. Mostly. Some are nearer than 50 light years. Some are hundreds of light years. A handful, the brightest stars in the sky, are the ones we can identify by name. Sirius, Vega, Arcturus, Polaris, Antares, Betelgeuse. Names that have come down to us through ancient civilizations, passed from culture to culture, attached to the same fixed points in the sky. But what you can see with your naked eye is a tiny, tiny fraction of what's out there. Maybe 2,000 stars at most on the clearest, darkest nights, far from any city, with perfect vision. 2,000 stars out of the 200 to 400 billion stars in our galaxy alone. That's less than a millionth of 1%. The rest of our galaxy, the vast majority of it, is invisible to your eyes. You'd need a telescope to see most of the stars in the Milky Way. And to see beyond the Milky Way into other galaxies, you need much more powerful instruments. The night sky you see is the visible tip of an iceberg, a small selection of the closest, brightest objects, drowned out by the much larger universe behind them. And even within what you can see, the perception of closeness is an illusion. Two stars that look right next to each other in the sky might be hundreds of light years apart, with nothing but empty space between them. The constellations are flat patterns we project onto a three-dimensional reality. Orion the Hunter, that familiar collection of stars, isn't really a hunter. The stars in his belt aren't actually near each other. They just happen to lie roughly along the same line of sight from our particular position in the galaxy. From any other vantage point, the constellation would dissolve into nothing recognizable. Think about what that means. The patterns we use to navigate The constellations we tell stories about, the shapes that have anchored human cultures for thousands of years, exist only from this one specific viewpoint. From any other star, the sky would look completely different. There would be no Orion, no Big Dipper, no Cassiopeia. The patterns we know are not universal. They're local, specific to where we sit. If we ever managed to reach another star, the night sky there would be alien. The familiar constellations would be gone. New ones would be visible, but you wouldn't know them. The cosmos would have to be relearned from scratch. Before we dive in, if you find this kind of deep exploration interesting, a like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's start with something humanity launched in 1977, back when most of us hadn't even been born yet. A small spacecraft about the size of a small car, with a few cameras, some scientific instruments, and a golden record bolted to its side. Voyager 1. Voyager 1 launched in September of 1977. Jimmy Carter was the President of the United States. The Soviet Union still existed. The first Star Wars movie had come out 4 months earlier. The personal computer revolution hadn't really started yet. There were no cell phones. There was no internet. The world Voyager 1 left was very different from the world we live in now. Voyager 1 was supposed to study Jupiter and Saturn and then probably die or fall silent. Its primary mission was a few years of close-up photography of the gas giants. Nobody really expected it to keep going forever. But the spacecraft just kept working, year after year. It flew past Jupiter in 1979, taking some of the most detailed photographs of that planet ever captured. It discovered active volcanoes on Io, one of Jupiter's moons, the first volcanic activity ever observed on a world other than Earth. It found evidence of a thin ring around Jupiter, something we hadn't known about. Then it kept going. It flew past Saturn in 1980, photographing the rings in detail no telescope on Earth could match. It studied Saturn's moon Titan, sending back data about its thick atmosphere. Then it kept going, and going, and going. The team that built Voyager 1 designed it to last. The components were chosen for reliability over decades, not years. The radiothermal generators, the things that produce its electricity, are powered by decaying plutonium. They produce a small but steady amount of energy that has been gradually decreasing over time. By 2025, the spacecraft is operating on about 30% of the power it had when it launched. NASA has had to shut down most of the instruments to keep the essential systems running. But the spacecraft is still alive, still sending back data, still listening for commands from Earth. In 1990, Voyager 1 took a photograph that became famous, the pale blue dot. From a distance of about 6 billion kilometers, Voyager 1 turned its camera back toward the inner solar system and photographed Earth. In the image, our entire planet appears as a single pale blue pixel, smaller than a grain of sand, suspended against the vast darkness of space. Carl Sagan wrote about that image. He called it a humbling reminder of our place in the cosmos. Every person who had ever lived, every war fought, every empire built, every love and every loss in human history, all of it happened on that single pale dot. From Voyager's vantage point, Earth was almost invisible, just a faint blue speck. That photograph was taken when Voyager 1 was about 5.5 light hours away from Earth. Not 5.5 light years, 5.5 light hours. The spacecraft has traveled about 4 times that distance since then, in the 35 years since the photograph was taken. It's still moving, still gaining ground, and from where it is now, even the pale blue dot photograph would be impossible to take. Earth is too small, too far, too lost in the glare of the sun for Voyager's camera to find. Earth, from Voyager's current distance, is essentially invisible. Voyager 1 has been traveling for nearly 50 years. By the time you watch this, it has been moving away from Earth every second for about half a century. It hasn't stopped to refuel. It hasn't slowed down. It has been gaining ground every moment of every day for almost 5 decades. And as of November of 2026, it will finally be one full light day away from Earth. Let me say that more slowly. The fastest, longest traveling spacecraft humanity has ever built has been moving outward for nearly 50 years at about 17 kilometers per second, which is over 60,000 kilometers per hour, which would carry you across the United States in about 4 minutes. At that speed, after 50 years of continuous travel, Voyager 1 is just now finally crossing the threshold where light from Earth takes a single day to reach it. A day. Light could travel from Earth to where Voyager 1 is right now in 24 hours. Voyager 1 took 50 years. Think about how small a single light day is in cosmic terms. The Sun is about 8 light minutes away from Earth. A light hour is 60 times that. A light day is 24 times that. So in cosmic distance terms, Voyager 1 is now 360 times farther from us than the Sun is. That sounds like a lot. It isn't. The nearest other star to our Sun is over 1,500 light days away. Voyager 1 hasn't even traveled 1/10,000th of 1% of the way to the nearest other star. Let's put that in human terms. If reaching the nearest star were a journey across a football field, Voyager 1, after 50 years of continuous travel, has moved less than the width of a single grain of sand from the goal line. Not the field, not the yard line, the goal line. A single grain of sand. How old were you when Voyager 1 launched? If you weren't born yet, that's fine. Voyager 1 has been traveling longer than you've been alive. Every birthday you've ever had, every relationship, every job, every place you've lived, every person you've loved and lost, all of it has happened while Voyager 1 was flying outward. It hasn't stopped during any of it. It's been moving the entire time. Every second of your life, that small spacecraft has been getting farther away, and it's just now reaching the boundary where signals take a day to travel. When NASA wants to send a command to Voyager 1, they have to wait 22 hours for it to arrive. Then they have to wait another 22 hours for any response. 2 full days for a single exchange. If something goes wrong with the spacecraft, by the time we know about it, 2 days have already passed. The situation could be completely different by the time we react. Voyager 1 has to handle most of its problems autonomously. It's too far away for us to help it in real time anymore. To put that delay into perspective, think about the much shorter delays we already deal with. When astronauts walked on the Moon during the Apollo missions, the round-trip communication delay was about 2.5 seconds. Each statement they made took a little over a second to reach Earth, and the response took a little over a second to come back. You can hear it in the recordings. Every exchange has that small, awkward pause. 3 seconds is not a long time, but it's long enough to disrupt the natural rhythm of conversation. The astronauts and mission control had to adapt their speaking style to account for the delay. When NASA controls rovers on Mars, the delay is much worse. At Mars's closest approach to Earth, when both planets are on the same side of the Sun, the delay is about 3 minutes each way. At the farthest distance, when Mars is on the opposite side of the Sun, the delay is about 22 minutes each way. So commanding a Mars rover involves planning each move in advance, sending the commands, waiting up to 44 minutes for a round trip, and then carefully analyzing the response before sending the next set of commands. You can't drive a Mars rover the way you'd drive a remote-controlled car. The delays are too long. Each operation takes hours. A drive of a few meters might take an entire day to plan, execute, and confirm. For Voyager 1, the delays are now 22 hours each way, a round trip of nearly 2 days. Anytime NASA wants to do something with the spacecraft, they have to plan 2 days ahead. Real-time control is impossible. Voyager 1 is essentially on its own out there, drifting silently, occasionally checking in with us, mostly just continuing on its predetermined trajectory. The golden record bolted to its side is a kind of message in a bottle. It contains greetings in 55 languages, samples of music from cultures across Earth, sounds of nature, mathematical diagrams, instructions for how to play it. Carl Sagan and a small team put it together in the 1970s, hoping that one day, perhaps millions of years from now, some alien civilization might find it. The record is meant to last for 1 billion years, if undisturbed. The contents of the golden record were chosen with great care. There are images of Earth, of human anatomy, of mathematical concepts, of solar system maps showing where Earth is. There are sounds, a baby crying, a kiss, footsteps, rain, animals. There is music, Bach, Mozart, Chuck Berry, traditional songs from cultures around the world. There are spoken greetings in dozens of languages, brief messages of welcome to whoever might find the record. President Jimmy Carter wrote a statement that's etched onto the record. The Secretary General of the United Nations at the time, Kurt Waldheim, also contributed a message. The record is designed to be playable. There's a stylus included. There are instructions encoded in pictograms showing how to put the stylus on the record and how to interpret the audio and image data. The instructions assume that any alien civilization advanced enough to find the spacecraft would be able to figure out how to decode the record, given enough time and effort. It's a poignant gesture. A tiny piece of human culture packaged up and thrown into the cosmic dark in the hope that someone, somewhere, sometime might find it and listen. The chances are essentially zero. The galaxy is huge, and Voyager 1 is tiny. The probability that any alien civilization will ever encounter it, let alone notice it, let alone decide to study it, is basically nothing. But it's still there, still flying, still carrying our voices outward into a universe that probably won't ever hear them. But here's the thing, Voyager 1 isn't really going anywhere. It's drifting. It's not aimed at any star. It's not on a course to encounter another civilization. The closest star, Voyager 1, will pass within a few light years of, in about 40,000 years, is a small red dwarf called Gliese 445. Not because Voyager 1 is heading there on purpose, just because that's what happens to be in the general direction of its motion. By the time Voyager 1 gets there, the spacecraft will have been silent for tens of thousands of years. Its power source will have died long ago. The cameras will be dust. The instruments will be inert. It will be a cold, dead piece of metal drifting through interstellar space. The golden record will still be there, still bolted to the side of the dead spacecraft, still ready to be played. Maybe alien hands will find it, decode it, listen to it. Probably not. Almost certainly not. The galaxy is huge, and Voyager 1 is one tiny object in it. The chances of anyone finding it are essentially zero. That's the start of our journey. The closest, most successful interstellar mission humanity has ever flown. 50 years of effort, 10 billion kilometers of distance, the farthest object we've ever pushed away from Earth. And it's barely outside the room. Past Voyager 1, in the direction it's flying, lies the Oort cloud. This is the boundary of the solar system, sort of. There are different ways of defining where the solar system ends. The heliopause is where the solar wind gives way to interstellar gas, and Voyager 1 crossed that in 2012. By that definition, Voyager 1 is technically already in interstellar space. But by another definition, the solar system extends out to wherever the sun's gravity is the dominant force on objects in the area, and that's much further. Out there, in the Oort cloud, are billions of frozen comets, faint, dirty snowballs that orbit the sun on paths so wide they take millions of years to complete a single circuit. The Oort cloud might extend halfway to the nearest star. Voyager 1 will take another 300 years just to reach the inner edge of the Oort cloud. It will take 30,000 years to cross it. 30,000 years. The first cities humans built were about 10,000 years ago. Voyager 1 will take 3 times as long to cross the comets at the edge of our own solar system as the entire history of human civilization combined. Voyager 1 isn't alone out there. Voyager 2 was launched in 1977 as well, slightly earlier than Voyager 1 in fact, on a slower trajectory that allowed it to visit Uranus and Neptune. It's the only spacecraft to ever fly past those distant ice giants. It's now the second farthest human-made object from Earth. Pioneer 10 and Pioneer 11, launched in 1972 and 73, are also out there, but their power has long since died. They're drifting silent through space, no longer transmitting, no longer receiving. New Horizons, the spacecraft that flew past Pluto in 2015, is also leaving the solar system, traveling outward, sending back faint signals from beyond the orbit of Pluto. 5 spacecraft, all heading out into interstellar space at different speeds, all aimed in different directions. None of them will reach another star. None of them will encounter anything resembling civilization. They'll drift for billions of years, slowly being battered by cosmic dust, eventually grinding down to atoms. The Voyagers, with their golden records, are designed to last the longest. They might survive for 1 billion years. But that's the maximum. After that, even they will be gone. 5 small spacecraft, 5 fragments of human aspiration, sent out into a galaxy that doesn't know we exist. The most ambitious thing our species has ever done. And from the perspective of the cosmos, they've barely moved. We haven't truly left home yet, and already the wall feels thick. Now, let's keep going. Let's leave Voyager 1 behind, drifting silently in its eternal night. And let's look at what comes next. The first other star. Proxima Centauri is a small, dim red dwarf about 4.24 light-years from Earth. By the standards of stars, it's not impressive. It's about 1/8 the mass of our Sun. It's so dim you can't see it with the naked eye, even though it's our nearest stellar neighbor. You need a telescope just to find it. But it's the closest. There is no star that is closer to us than Proxima Centauri. Everything else in the universe is farther away. 4.24 light-years. Proxima Centauri is part of a triple star system. The other 2 stars, Alpha Centauri A and Alpha Centauri B, are similar to our Sun. They orbit each other in a tight pair. Proxima orbits them at a much greater distance, taking about 500,000 years to complete a single orbit around the inner pair. From Earth, when you look toward the constellation Centaurus, all 3 stars appear close together in the sky, but they're spread across light-month distances within the system itself. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. They called it Proxima b. It's roughly Earth-sized, possibly rocky, and it orbits in what's called the habitable zone, the distance from its star where liquid water could potentially exist on the surface. It's a candidate for life. Maybe. Probably not. Given the harsh environment around red dwarfs, the radiation flares, the tidal locking that would keep one side permanently facing the star and the other side permanently in darkness. But it's possible. It's the nearest exoplanet to Earth, and it might be habitable. 2 more planets have been confirmed since then. Proxima c is a larger world farther out, beyond the habitable zone. Proxima d is a small inner planet too close to its star to be habitable. 3 confirmed planets around the nearest star to our Sun. Maybe more we haven't detected yet. If we wanted to send a probe to look at Proxima b, to study its atmosphere, to find out whether it has water, whether it has life, we could try. But the journey is impossible at the speeds we can currently achieve. Let me try to make that real. Light takes 4.24 years to travel from Proxima Centauri to Earth. Light, the fastest thing in the universe, the thing that nothing in physics can exceed. Even light, going as fast as anything can possibly go, takes 4 years and a few months to make that journey. The light hitting your eyes from Proxima Centauri tonight left that star in 2022. Whatever was happening to Proxima Centauri in the years since then, you can't see yet. The light hasn't reached you. Whatever happens to the star tonight, you won't see for another 4 years. That's not a long time on cosmic scales. 4 years is nothing. The universe has existed for nearly 14 billion years. 4 years is an eye blink. But for humans, 4 years is a long time. 4 years ago, the world was a different place. You were a different person. Light has been traveling toward Earth from Proxima Centauri continuously for those 4 years, and only now arriving. There's no shortcut. There's no way to get information faster. So how would you actually get there? At Voyager 1 speed, about 17 kilometers per second, the journey would take roughly 75,000 years. Let me say that again. 75,000 years of continuous travel through the empty void between stars, with nothing to slow you down, no planets to refuel at, no aliens to talk to, just empty, dark, silent space for the better part of 100,000 years. How many human generations is that? If we say a human generation is about 30 years, 75,000 years is roughly 2,500 generations. 2,500 generations of humans, born and dying inside that spacecraft, never seeing Earth, never seeing Proxima Centauri, just traveling through the dark. The first human ship to reach Proxima Centauri, if we built one tomorrow at Voyager 1 speeds, would arrive carrying the descendants of the people who launched it, 2,500 times removed. They wouldn't know what Earth looked like in any meaningful sense. They would have grown up inside a metal tube, hearing stories about a planet they had never seen. Whatever traditions you have, whatever culture you grew up with, whatever language you speak, would have drifted and changed and possibly been replaced entirely over so many generations of isolation. The arriving crew might not even recognize themselves as human in the way you think of human. They would have evolved, both biologically and culturally, in directions you cannot predict. Imagine being born on that ship. You wake up in a metal corridor. Your parents tell you stories about a place called Earth, a blue and green world they've never seen, where the sky is open and you can walk for miles in any direction without hitting a wall. You don't believe them. The stories don't match anything in your experience. The ship is your entire universe. The recycled air, the artificial light, the same 100 faces you've known your whole life, the same hum of the engines that has always been there. That's what reality is to you. Earth is a fairy tale. The arrival in 3,000 years is something your great-grandchildren will worry about, if anyone is still bothering to navigate by then. Generations on the ship would face strange choices. The mission was set by ancestors who lived and died centuries ago. By generation 100, do you still feel obligated to keep going? By generation 500, why are you still flying toward this star? By generation 1000, has the mission's original purpose been lost? Have your descendants forgotten why anyone built the ship in the first place? Or worse, have they decided to turn around, to go back to Earth, only to find that they don't know how to get there anymore? That the navigation systems require knowledge no one alive remembers anymore? That they're stuck, drifting, between the place they came from and the place they were going, with no way to reach either? This is what real interstellar travel looks like. Not a quick trip, not a movie scene where the captain says, "Set course for Proxima Centauri," and they arrive in a few hours. A multi-millennium voyage of people born to keep going, trapped in a vessel they did not choose, aimed at a star they will never see in their lifetimes. There are proposals to do it faster. The most famous is something called Breakthrough Starshot, announced in 2016. The idea is to use enormous laser arrays on Earth to push tiny spacecraft, each weighing maybe a gram, attached to ultra-thin reflective sails, accelerating them to about 20% of the speed of light. At that speed, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for the signals to come back, and you could potentially get data from Proxima Centauri in 24 years from launch. That's within a human lifetime. You could launch a mission when you're young and possibly see results before you die. But the engineering challenges are enormous. The laser array would need to produce about 100 gigawatts of power, the equivalent of about 100 nuclear power plants, all focused into a single coherent beam. The probe would need to be incredibly light, basically a chip with a transmitter, but also robust enough to survive the radiation and dust impacts at 20% of light speed. At that velocity, even a grain of dust hits with the energy of a small bomb. The probe needs shielding, but shielding adds weight, and weight is the enemy of acceleration. Every gram you add requires more laser power. The math compounds against you. Even if we built it tomorrow, the probe wouldn't slow down at Proxima Centauri. It would fly past at 20% of light speed, taking maybe a few hours of useful data, and then continue into the void on the other side, never to be seen again. One shot. No second chances, no ability to orbit or land or study anything in detail. Just a flyby at relativistic speed, capturing what it can, then gone forever. There's another proposal called Project Daedalus, designed in the 1970s by the British Interplanetary Society. It would use nuclear fusion engines to accelerate a much larger spacecraft, possibly carrying instruments and cameras, to about 12% of light speed. The journey would take about 50 years one way. The technology required, controlled nuclear fusion at scale, doesn't exist yet. It might never exist. We've been trying to harness fusion power for over 70 years, and it remains stubbornly out of reach. Then there's Project Icarus, a more recent design, similar concept, but with refined engineering. It would also take decades to reach the nearest star. None of these projects have been built. None of them are likely to be built in our lifetimes. They're paper studies, blueprints for a future that might never come. And this is for the closest star, the very nearest neighbor we have. Anything beyond Proxima Centauri requires even more time, even more energy, even more compromise. The Alpha Centauri system, of which Proxima Centauri is a part, contains two other stars, Alpha Centauri A and B, similar to our Sun. They orbit each other. Proxima orbits them at a much greater distance, taking hundreds of thousands of years to complete a single orbit. If you wanted to visit all three stars in the system, you'd have to travel between them too, and the distances inside the system, while smaller than the gap between systems, are still vast. Past Alpha Centauri, the next closest star is Barnard's star, about 6 light-years away. Then Wolf, 359. Then Lalande, 21185. Then Sirius, each one a little farther, each one harder to reach. Most of them red dwarfs you can't see with the naked eye, most of them silent, drifting, alone. Within 20 light-years of Earth, there are about 130 known stars. Most are red dwarfs, a few are sun-like. Each one might have planets, some of them probably do. We've found exoplanets around many of them already. There might be Earth-like worlds within 20 light-years of where you're sitting right now. But 20 light-years, at Voyager 1 speeds, is 350,000 years. Even at 20% of light speed, it's 100 years. Multiple generations, even at the fastest theoretical speeds we've imagined. The closest neighborhood is, in any practical sense, exile. Even the closest exit door requires generations to walk through. That's the reality of stellar distance. Now, let me show you what that distance does to time. The light from Proxima Centauri takes 4 years to reach you. So when you look at it, you're looking 4 years into the past. Whatever happened to that star in the last 4 years, you have not seen yet. You won't see it for years to come. The version of Proxima Centauri you observe is an outdated copy, an echo of what the star was before, projected through the long delay of light travel. This is true for every star you can see, every single one. The light from each one is older than the moment you receive it. Some are older by years, some are older by decades, some are older by centuries. Sirius is the brightest star in the night sky. It's about 8.6 light-years away. So when you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. If you're 20 years old, you're seeing Sirius as it was when you were just over 11 in middle school. If you're 40, you're seeing it as it was in your early 30s. The Sirius you see is Sirius from a time you've already lived through, but it's a Sirius you couldn't have seen back then because the light hadn't arrived yet. The gap between then and now is the wall. Vega is a bright star about 25 light-years away. If you're 25 years old, the photons hitting your eyes from Vega tonight left that star around the time you were born. When they began their journey, you didn't exist. Your parents may have looked up at the same star around then, glimpsing photons that had departed 25 years earlier when they were children themselves, generations layered on top of each other through the long delay of starlight. Imagine your grandmother as a child, looking up at Vega. She would have caught light that departed 25 years before her birth, at a time when neither she nor your mother existed. Imagine your great-grandmother doing the same thing decades earlier, each generation looking at the same Vega, catching light from a different era. The star itself doesn't notice. The star has been there the whole time, doing whatever stars do, indifferent to which humans happen to be looking at it. But each human gets their own version of Vega, lit by photons from 25 years before their moment of looking. The star is a mirror that always reflects the past. Arcturus, the bright orange star in the constellation Boötes, sits about 37 light-years away. The photons arriving here tonight began their journey when the world was a different place. The internet was just becoming widespread. Cell phones were rare and expensive, old enough that an entire generation has grown up since that light started its trip. Children born when those photons left have grown into adults, started careers, had children of their own. All of that human time, while a single beam of starlight crossed the gap between Arcturus and Earth. Rigel, The bright blue star at the foot of Orion is much farther away than its companion Betelgeuse, somewhere around 860 light-years. Photons reaching us from it tonight set out around the year 1200, the medieval era. Before the printing press, before Columbus, before any modern nation existed, Genghis Khan was conquering most of Asia when that light departed. The Crusades were ongoing, a different planet of humans in a different time, never knowing that their starlight would eventually reach the eyes of beings sitting in front of glowing rectangles 700 years later. Deneb, the brightest star in the constellation Cygnus, is one of the most distant stars visible to the naked eye. It's about 2,600 light-years away. Light from Deneb that you see tonight began its journey around 600 BCE, before the Roman Empire, before Christianity, before Buddha, around the time of the ancient Greek philosophers Pythagoras and Confucius. The light you see tonight is older than every world religion that exists today. Polaris, the North Star, sits about 445 light-years away. The photons entering your eyes from it tonight departed in the early 1600s. Sometime around when the first English colonies were being established in North America, before Jamestown, before Plymouth Rock, before there was a United States, before most modern nations existed. William Shakespeare was alive when that light set out from Polaris. He was writing his plays. He wouldn't write Hamlet for another 2 years. The light from Polaris, in your eyes tonight, is older than every modern country in the world. And you receive it casually, glancing up at the sky to find north, treating it like just another light. Betelgeuse is a red supergiant, the bright reddish star marking the upper shoulder of Orion. It's about 550 light-years away. The light from Betelgeuse you see tonight left that star in 1474. Christopher Columbus was 23 years old. He hadn't sailed yet. The Italian Renaissance was happening. The printing press had been invented just 2 decades earlier. Most of Europe was still emerging from the Middle Ages. Leonardo da Vinci was 22 years old, working as an apprentice. Michelangelo wouldn't be born for another year. When that light started traveling, the modern world didn't exist. There were no cars, no computers, no modern medicine, no modern science, no modern anything. There were horses and ships and swords and people who believed the Earth was the center of the universe. And tonight, in this moment, that ancient light enters your eye. But here's the thing about Betelgeuse. It's a massive star nearing the end of its life. It's expected to explode as a supernova sometime in the next 100,000 years, which on cosmic timescales is essentially immediate. When it does, it'll briefly outshine the full moon, visible during the day, one of the most spectacular astronomical events humans have ever seen. But it might have already exploded. That's the thing. The light from Betelgeuse that we see is from 1474. We're seeing the star as it was over 500 years ago. Whatever happened to it since then, we don't know. Maybe it exploded in 1500, maybe in 1600, maybe last week. We won't see the explosion until the light from it travels the 550 light-years to reach us. So if Betelgeuse exploded in 1700, we won't witness it until around 2050. The star you can see tonight as a steady reddish point of light might already be gone, already collapsed, already ended. We're seeing a ghost. We're looking at a star that, in the present moment of the universe, may not exist anymore. We just don't know yet. This applies to every star far enough away. The constellations you see in the night sky are not the constellations as they are now. They're the constellations as they were at various points in the past, layered together to form a single image. Some of the stars you see have already changed dramatically. Some have probably died. Some have moved through space far enough that their position is no longer where the light suggests. The night sky is a composite of different times, all blended into one apparent moment, none of it actually current. Pause for a moment. Walk outside if you can. Look up at the sky, even briefly. Every point of light up there started its journey years ago, decades ago, centuries ago, millennia ago. Some of it left before any human you know was born. Some of it left before nations existed. You're standing in a rain of ancient photons, all carrying messages from times you'll never live in, from stars whose present moments you'll never see. It's a kind of horror when you sit with it. The universe never lets you have the present. Let's keep going. Past the nearby stars, past the bright lights of our local galactic neighborhood, we go. Our galaxy, the Milky Way, is a flat spiral disk of stars, about 100,000 light years across, containing somewhere between 200 billion and 400 billion stars. We sit in one of the spiral arms, about 26,000 light-years from the galactic center. The Milky Way is enormous on its own terms. The light from the center of our own galaxy left 26,000 years ago. When that light departed, humans were still hunter-gatherers. Agriculture hadn't been invented. There were no cities, no writing, no civilization. The light from the heart of our home galaxy is older than every human invention, every culture, every memory we've ever recorded. But the Milky Way is just one galaxy. There are others around us. Andromeda is the nearest large galaxy to ours. It's about 2.5 million light-years away. It's so far that we can barely see it with the naked eye, even though it's larger than our own galaxy. On a clear, dark night, away from city lights, Andromeda appears as a faint smudge in the sky, about 3 times the angular width of the full moon. It's the most distant object a human being can see without a telescope. 2.5 million light-years. When the light from Andromeda you see tonight began traveling, our human ancestors were not yet humans in any modern sense. They were early Homo, not Homo sapiens. We don't know exactly which hominid species was around 2.5 million years ago. Maybe Homo habilis, the earliest stone tool users. Maybe Australopithecus. They were small, ape-like, living in scattered groups across the African savanna. They were figuring out how to chip stones into sharp edges. They were learning to use fire, possibly. They had no language as we understand it, no art, no clothing, no agriculture, nothing. That light has been traveling toward Earth for the entire history of the human family. Through every species we evolved through every migration out of Africa, through every culture that has risen and fallen, through every war and every peace, and every birth and every death. The Andromeda light, having started its journey when our ancestors were not yet our ancestors, is still arriving, still hitting your eyes tonight, still bringing news of a galaxy 2.5 million years out of date. Andromeda is moving toward us. It's gravitationally bound to the Milky Way, falling toward us at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin to collide. The collision won't be sudden. It'll unfold over hundreds of millions of years. The two galaxies will pass through each other, swing back, pass through again, and eventually merge into a single elliptical galaxy. Direct collisions between individual stars will be rare, because the spaces between stars are so vast that even two galaxies passing through each other is mostly empty space, moving through empty space. But the gravitational disruption will be enormous. The familiar shape of the Milky Way will be torn apart. The night sky on Earth, if any humans are still around to see it, will be filled with the bright stars and dust lanes of Andromeda gradually overlapping our own view. Astronomers have already given the merged galaxy a name, Milkomeda. The two galaxies will become one. The Milky Way, as we know it, will cease to exist. But that's billions of years away. By the time it happens, the Sun will be in the late stages of its life. Earth might already be uninhabitable. Whatever beings might witness, the merger will not be us, or anything we can recognize. The Milky Way and Andromeda are the two largest galaxies in our local group. There are dozens of smaller ones around us, dwarf galaxies orbiting the Milky Way and Andromeda, slowly being torn apart by the gravity of their larger neighbors. The Large Magellanic Cloud and the Small Magellanic Cloud are visible from the southern hemisphere as bright patches of light. They're satellite galaxies of the Milky Way, both being slowly pulled apart and absorbed. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud, about 200,000. Within them are billions of stars, vast nebulae, and possibly civilizations we'll never reach. The Triangulum Galaxy is the third largest in the local group, about 3 million light-years away, smaller than the Milky Way and Andromeda, but still containing tens of billions of stars. It's also gravitationally interacting with Andromeda and might eventually merge with it before the larger Milky Way collision happens. The local group is about 10 million light-years across. It contains maybe 100 galaxies, most of them small. Most of them dwarf galaxies orbiting the larger ones, slowly being consumed. That's our home neighborhood, and it's a tiny pocket of a much larger structure. Our local group is part of a supercluster called Laniakea, which contains thousands of galaxies and is over 500 million light-years across. Laniakea is a Hawaiian word meaning immeasurable heaven. It's the largest structure to which our local group belongs, defined by the gravitational flow of galaxies toward a region called the Great Attractor, hidden behind the disk of our own galaxy. Beyond Laniakea, there are other superclusters. The Virgo supercluster, the Hydra Centaurus supercluster, the Pisces Cetus supercluster. Beyond those, there are filaments and walls of galaxies stretching for hundreds of millions of light-years more. The cosmic web, the actual structure of the universe at its largest scales. A vast network of bright filaments separated by enormous dark voids, with galaxies clustering along the threads. And our radio signals, the messages we've been sending out into space for about a century, have only reached the nearest 100 light-years, maybe 200, out of 100,000 light-years across our galaxy alone, out of 2.5 million light-years to Andromeda, out of billions of light-years to the edge of the observable universe. If aliens are out there, if intelligent life exists in some other corner of the cosmos, our voices haven't reached them yet. The early radio broadcasts from the 1920s have traveled about 100 light-years. They've passed through a small bubble of space containing maybe a few thousand stars at most. A tiny fraction of our galaxy, an infinitesimal fraction of the universe. We're a faint whisper in a vast, silent room. And even if our whisper has been heard, the response can't reach us in any reasonable time. If there's a civilization 50 light-years away, listening, deciding to reply, their response would take 50 more years to come back. A round trip of a century for a single exchange. By the time their reply arrives, we'd have completely changed as a civilization. They'd be replying to who we used to be. We'd be receiving a message from who they used to be. The conversation would be incoherent. That's if anyone is even listening. Most stars are too far away to hear us at all. Our radio signal bubble is a tiny patch of the galaxy, and even within it, Our signals are getting fainter and fainter as they spread out. By the time they reach a star a few dozen light-years away, they'd be almost impossible to detect against the background noise of space, even with very sensitive equipment. We might be alone, or we might be in a galaxy full of life, none of which knows we're here, none of which we'll ever talk to. Now, let me tell you about something that happened in 1977, and the question it raised, which has never been answered. A man named Jerry Eman was working at the Big Ear radio telescope at Ohio State University. The telescope was part of an early SETI effort, the search for extraterrestrial intelligence. Day after day, the telescope was recording radio signals from various directions in the sky, mostly background noise, looking for any unusual pattern that might suggest a deliberate transmission from somewhere else in the galaxy. On August 15th of 1977, the telescope picked up a signal from the direction of the constellation Sagittarius. The signal lasted 72 seconds. It was much stronger than the surrounding noise. It was at a very specific frequency, near the natural emission line of hydrogen, which is the kind of frequency a civilization deliberately trying to communicate might choose because hydrogen is the most common element in the universe. When Eman saw the printout of the data, he circled it with a red pen and wrote a single word in the margin: "Wow." That's why we call it the wow signal. The signal lasted 72 seconds, and then it was gone. The telescope was scanning the sky in such a way that it should have picked up the signal again 3 minutes later, when it pointed back at the same patch of sky. But the signal wasn't there. It had vanished. Astronomers have been looking for the wow signal ever since. It's been over 40 years. They've used much more sensitive telescopes. They've pointed them at the exact same patch of sky, again and again, listening at the exact same frequency. They've expanded the search to nearby frequencies, to nearby regions of the sky. They've used multiple instruments around the world, coordinating to listen for any hint of the signal returning. Nothing. The signal has never repeated. Whatever sent it was either a one-time event or a signal that swept across our region of the galaxy briefly and then moved on. Like a lighthouse beam rotating, illuminating any one place for only a moment before continuing to scan elsewhere. This is the lighthouse problem. If aliens are out there, if they're broadcasting, the signals might not be aimed at us. They might be sweeping across the sky, illuminating different stars at different times, the way a lighthouse beam rotates. From our perspective, we'd see the signal briefly, then nothing. We wouldn't know whether to expect it to come back. We wouldn't know how long the cycle was. We wouldn't know which of the millions of stars in the right direction was actually the source. There have been other unusual signals over the years. Fast radio bursts, brief, intense pulses of radio energy detected from distant galaxies, were once mysterious, but have now been mostly attributed to natural phenomena like magnetars, highly magnetized neutron stars. The Lorimer burst in 2007 was the first one detected. Since then, hundreds more have been found. Most appear to be natural, though one repeating fast radio burst has caused some debate. None has been definitively linked to alien intelligence. In 2020, a candidate signal was detected from the direction of Proxima Centauri. It was called BLC-1, Breakthrough Listen Candidate 1. It was a narrow frequency signal, the kind that could be artificial, coming from the direction of our nearest stellar neighbor. Excitement was high for a while. Eventually, after careful analysis, the signal was determined to most likely be terrestrial interference, probably from a malfunctioning piece of equipment or a satellite. The cosmos remained silent. The wow signal stays the most intriguing because we still don't have a good explanation for it. There have been proposed natural explanations. Maybe two comets that were in that region of the sky at the time were emitting the signal somehow. The hypothesis was that the comets had hydrogen clouds around them that briefly resonated at the right frequency. But this idea has been challenged by other astronomers who say the math doesn't work out. Comets don't usually produce signals that narrow in frequency. The WOW signal had a very specific frequency, much narrower than what natural sources usually produce. That narrowness is a hint that whatever made it was something deliberate, something engineered to be at exactly that frequency. But we don't know. We may never know. The signal lasted 72 seconds in 1977 and never came back. It might have been an alien beacon. It might have been a passing satellite. It might have been a glitch in the equipment. Decades of investigation have not given us a definitive answer. And here's the deeper problem. Even if we identified the source, even if we figured out that the signal came from a specific star 100 light-years away, we couldn't have a real conversation. 200 years for a round trip. That's longer than most civilizations might survive. By the time we received a reply, the people who sent it might be gone. Their planet might have died. Their star might have been destroyed. Or they might be so culturally different from when they sent the original message that they don't even remember sending it. Communication across cosmic distance becomes archaeological. You're not having a conversation. You're studying records left by something that probably no longer exists, replying with messages that the recipients, if there are any, will only receive long after you're dead. This is why the universe might be silent, even if it's full of life. Civilizations rise and fall on timescales much shorter than the time it takes light to cross the galaxy. We've only been broadcasting for a century. We don't know if we'll still be broadcasting in another century, let alone in 1,000 years. Maybe every civilization gets a brief window where they shout into the cosmos, and that window closes before any other civilization happens to be listening at the right frequency in the right direction. The universe might be full of voices, all of them too far apart, too brief, too out of sync to ever connect. There might be lighthouse signals from civilizations that died 1,000 years before we ever invented radio. There might be civilizations right now sending signals that won't reach us for another 1,000 years, by which point we might have changed beyond recognition or vanished entirely. The cosmic conversation, if there is one, is happening across timescales that don't fit human lives or human civilizations. There's an idea in physics called the Great Filter. The argument goes like this. The universe seems full of potentially habitable worlds. Many stars have planets. Many planets are in the habitable zone. Some of those planets probably have liquid water. Some probably have organic chemistry. Some might have life. Some of that life might evolve to intelligence. Some of that intelligence might develop technology. Some of that technology might reach across stars. But we don't see anyone. The night sky is full of suns, but it's silent. No megastructures, no clearly artificial signals, no probes from elsewhere. Nothing but stars doing what stars do. This is the Fermi paradox. If life is so common, where is everyone? One answer is the Great Filter. There must be some step in the chain from habitable planet to interstellar civilization that almost no species crosses. Maybe life itself is rare. Maybe intelligence is rare. Maybe technological civilizations are rare. Maybe interstellar civilizations destroy themselves before they get anywhere. Whatever the filter is, it's somewhere along the path, and most species never make it past. Another answer is the lighthouse problem. Maybe civilizations exist even commonly, but they're brief. They appear, develop technology, broadcast for 1,000 years or so, and then either go extinct or stop broadcasting. The universe is silent because the windows of broadcasting are short and rare and don't overlap. Another answer is that they're hiding. Maybe contacting other civilizations is dangerous, and any species that announces itself to the cosmos gets destroyed. The dark forest hypothesis. The universe is full of life, but everyone has learned to be silent because announcing yourself is suicide. The dark forest hypothesis comes from a science fiction novel by the Chinese author Liu Cixin, but the underlying logic has been debated by serious scientists. The reasoning goes like this. If life is common, then aggressive life is probably common too. Some civilizations might decide that any other civilization is a potential threat, since you don't know what they'll do once they get advanced enough to compete with you for resources. The safest strategy, given that uncertainty, is to destroy any other civilization you find. Strike first. Don't negotiate. Don't communicate. Just eliminate the potential threat. If even a small fraction of civilizations adopt this strategy, then announcing yourself to the cosmos becomes suicidal. Any signal you send out is an invitation to be hunted. Any radio bubble expanding from your planet is a beacon for predators. The civilizations that have learned this lesson are silent. They listen, but they don't broadcast. They look, but they don't shine. The terrifying implication is that we on Earth have been broadcasting for over 100 years. Our radio signals have been spreading out into space, advertising our existence to anything within 100 light years that might be listening. If the dark forest hypothesis is correct, we may have already attracted attention. The response might be on its way. We just don't know it yet. Or maybe the hypothesis is wrong, and the silence is for some other reason. Maybe civilizations don't last long enough to coordinate galactic-scale aggression. Maybe interstellar travel is so hard that no one bothers with hunting. Maybe we're just early, and most civilizations haven't developed yet. We don't know. We're guessing. The cosmos doesn't tell us its secrets. Another answer is that we're alone. Maybe Earth is unique. Maybe we're the only intelligent species in the galaxy, or even the universe. Maybe all those potentially habitable planets never developed life, or the life never developed beyond simple cells, or the intelligent species all wiped themselves out before getting to interstellar distances. We don't know which answer is right. We may never know. The cosmic distances are too vast, the times too long, the silence too persistent. We might not be alone. We might just be unreachable. Now we come to the largest section of this video, the most important part, the thing that, more than anything else, makes cosmic distance genuinely terrifying. The cosmic wall. The universe is expanding. This isn't a metaphor. It's a physical fact, measured precisely, observed in countless ways. The space between galaxies is stretching. Distant galaxies are receding from us. The farther away a galaxy is, the faster it's moving away. The expansion has been going on since the Big Bang, nearly 14 billion years ago. And in the last few billion years, the expansion has been accelerating, driven by something we call dark energy, which we don't really understand, but whose effects we can measure. Edwin Hubble figured this out in 1929. He observed that distant galaxies were redshifted. The light from them was stretched to longer wavelengths, exactly the way you'd expect if those galaxies were moving away from us. The farther away the galaxy, the more the light was redshifted. He plotted the data and found a clear linear relationship. More distant galaxies were receding faster. The universe was expanding. Before Hubble, most astronomers had assumed the universe was static, eternal, unchanging. Even Einstein had introduced a fudge factor into his equations, the cosmological constant, to keep the universe from collapsing or expanding. He called it his greatest blunder later in life, after Hubble's discovery showed that the universe was, in fact, dynamic, expanding, changing. Hubble's work was building on observations made a few years earlier by Vestos Slipher, who had noticed that most galaxies were redshifted but hadn't yet linked the redshifts to distances. The combination of Hubble's distance measurements with Slipher's redshift data gave us the modern picture of an expanding universe. Other astronomers, including Georges Lemaître, had proposed expanding universe models from theory before Hubble confirmed them with observation. Lemaître, a Belgian priest and physicist, had even predicted what we now call the Hubble constant, the rate of expansion before the data was in to support him. He called the early universe a primeval atom and suggested everything had begun from a single dense state. The Big Bang theory, basically, in its earliest form. But what Hubble observed in 1929 was just the beginning. In 1998, two teams of astronomers studying distant supernovae made an even more startling discovery. The expansion of the universe wasn't just continuing, it was speeding up. Galaxies weren't just moving away, they were moving away faster than they used to. Something was pushing them apart faster than gravity could pull them together. Something was overcoming the gravitational tendency for matter to collapse on itself. We don't know what that something is. We call it dark energy because we can't see it, can't detect it directly, can't explain what it is. We can only measure its effects. About 68% of the total energy in the universe is dark energy. The rest is matter, both ordinary and dark. The dark energy is everywhere, evenly distributed, pushing space apart at every point. It doesn't dilute as space expands. It maintains its density even as the universe grows. The more space there is, the more dark energy there is, and the faster the expansion accelerates. It's a runaway process. The implications are staggering. Whatever dark energy is, it's the dominant component of the universe by far. The stuff we can see, the stars and gas and dust and galaxies, is less than 5% of the total. Dark matter, the invisible material whose gravity holds galaxies together, is about 27%. The rest, 2/3 of everything, is this mysterious dark energy that's driving the universe apart. We don't know if dark energy is constant or if it changes over time. We don't know if it's a property of space itself, like Einstein's cosmological constant, or some kind of evolving field that might shift in the future. The fate of the universe depends on these answers. If dark energy is constant, the expansion will continue at its current accelerating rate, and the universe will end in something like the cold, dark, isolated future I described earlier. If dark energy gets stronger over time, the expansion could become so fast that even atoms get torn apart in a scenario called the Big Rip. If dark energy weakens, the expansion could eventually reverse, ending in a big crunch where everything collapses back together. Right now, our best evidence suggests dark energy is roughly constant. The cold, slow death is the most likely scenario. But we're not certain. The universe might surprise us. The future is genuinely unknown. Here's what that means in practical terms. For nearby galaxies, the expansion is small. The Andromeda Galaxy is actually moving toward us, not away because it's gravitationally bound to the Milky Way, and the local pull is stronger than the cosmic expansion. Within our local group, gravity wins. The galaxies stay together. They'll eventually merge. They're not going anywhere. But beyond our local group, the expansion is dominant. The Virgo cluster, 53 million light-years away, is receding from us. The Coma cluster, 300 million light-years away, is receding faster. The Hercules cluster, even farther, faster still. The pattern is consistent. The farther a galaxy is, the faster the space between us is expanding, and the faster the galaxy appears to be moving away. For galaxies far enough away, The expansion of space is happening faster than the speed of light. This sounds impossible. Nothing can move faster than light. That's the cosmic speed limit. But the galaxies themselves aren't moving faster than light through space. The space between us is expanding, and the cumulative expansion across vast distances adds up to apparent motion faster than light. The galaxies aren't violating physics. The space itself is. Think of it this way. Imagine ants walking on a balloon. The ants can only walk at a certain maximum speed. But if you're inflating the balloon, the surface itself is expanding underneath them. Ants on opposite sides of the balloon might be moving away from each other faster than either of them could walk, simply because the balloon is growing. That's roughly what space is doing. The galaxies are sitting in space, mostly moving slowly relative to their local environment. But space itself is stretching, carrying the galaxies along with it. At large enough distances, the cumulative stretching exceeds the speed of light. What this means is that there are galaxies in the universe whose light will never reach us. Ever. Not in a billion years. Not in a trillion. Never. Right now, you can look out and see galaxies billions of light years away. You can see their light. That light has been traveling for billions of years to reach you. It's old light. It's information about the universe as it existed when those galaxies were younger than they are now. But the universe is expanding while the light is traveling. The galaxies the light came from have been receding from us the entire time. Some of them by now are receding so fast that any new light they emit will never catch up to us. Their current selves are already cut off from our future. We can see what they were, but we'll never see what they are. The cosmic event horizon is the boundary beyond which this happens. It's a sphere around us, about 16.5 billion light-years in radius, beyond which expansion is faster than light can travel through it. Anything past that horizon is, by definition, unreachable. Any signal from beyond the horizon can't get to us. Any signal we send can't get to them. The relationship between us and them is permanently severed. Here's the part that keeps cosmologists up at night. The cosmic event horizon is shrinking. In the time it takes you to watch this video, several galaxies will slip over it, cut off from us forever. Tomorrow, more. Next month, more. In 1,000 years, a measurable number. In 1 billion years, vast regions of the current observable universe will be unreachable. Right now, today, 94% of the galaxies we can see in our telescopes are already permanently beyond reach. Their light still arrives because the light was emitted long ago when they were closer. But their current positions are already past the cosmic event horizon. Anything that happens to those galaxies now, we will never see. Anything we want to send to them, we cannot. They are visible but unreachable, lit by light that was already in transit before the doors closed. 2 trillion galaxies are estimated to exist in the observable universe. Of those, only about 120 billion are still within our reachable horizon. The rest, more than 90%, we can see but never visit, even with infinite time, even with infinite technology, even with any conceivable propulsion system. The expansion of space has already cut us off from the vast majority of what we can see. Think about the Hubble Deep Field Photograph. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of the sky for 10 consecutive days. The patch was about 1/24 millionth of the total sky. A speck. They expected to see darkness. Instead, the camera captured over 3,000 galaxies in that single tiny patch. Galaxies of every shape and size and age, scattered across the depths of cosmic time. Some were nearby, relatively speaking, just a few billion light years away. Others were so distant that the light had been traveling for over 12 billion years to reach the telescope, almost as old as the universe itself. If you extrapolate the density of galaxies in that one patch out across the entire sky, you get the staggering estimate of over 100 billion galaxies in the observable universe. Later, refinements pushed the estimate to 2 trillion. Each galaxy contains billions of stars. Each star may have planets. The cosmic abundance is overwhelming, and almost all of it is unreachable. The galaxies in the Hubble Deep Field are mostly past our cosmic event horizon by now. We can see what they were billions of years ago when the light started. But what they are now, in their current present moment, is forever beyond reach. The light from their current selves will never make it to us. The expansion is too fast. The distance is too great. Imagine being able to see a beautiful place, but never being able to visit it. Not because of money or politics or distance you could theoretically cross, but because of physics. Because the very space between you and that place is stretching faster than light can travel through it. The place is real, it exists, it's beautiful, and you will never, ever get there. No technology will ever let you. No effort will ever pay off. The universe itself has placed it beyond you. That's most of what we see in the night sky, most of the galaxies in the Hubble images, most of what telescopes will ever find. We get to look, we don't get to touch. You were born into a universe that had already given up on most of itself. It gets worse. In the far future, billions of years from now, the expansion will be so dominant that even the light from those distant galaxies will redshift beyond detection. The galaxies that are currently visible will fade and vanish. They won't disappear suddenly. They'll just gradually become so redshifted that no instrument can detect them anymore. Their light will still be traveling, but stretched to such long wavelengths that it's effectively gone. Astronomers in the deep future, perhaps 100 billion years from now, will look out into a universe that appears almost empty. The Milky Way and Andromeda will have merged into a single elliptical galaxy, sitting alone in a dark sky. Beyond it, nothing. No other galaxies visible. No cosmic background. No evidence of the Big Bang. No evidence of an expanding universe. No evidence that any of the structure and complexity we see today ever existed. Future astronomers will look at their sky and conclude that the universe is small, simple, and unchanging. They will have no way to know they are wrong. The evidence will have receded beyond all possibility of detection. The expansion will have erased the cosmic past from view. We are living in a privileged moment. The universe is young enough that we can still see most of what's out there. We can still see the cosmic microwave background, the afterglow of the Big Bang. We can still see distant galaxies billions of light years away. We can still measure the expansion of the universe and learn about its history. None of these things will be possible in the deep future. Civilizations that arise then will have a much smaller, much sadder cosmos to study. They won't know about the rest. They won't even know to look. Every second of your life, more galaxies slip away. Every breath you take, the universe is forgetting some of itself. The cosmic horizon is closing, and once a galaxy crosses it, no power in the universe can bring it back. You were born into a universe already waving most of itself goodbye. Think about what's happening right now, in this very moment. There are galaxies you can see in photographs from the Hubble Space Telescope, the James Webb Space Telescope. Galaxies that look beautiful, structured, full of stars and worlds and possibly civilizations. The light from them has been traveling toward us for billions of years. It arrives, and we marvel at the images. But the galaxies themselves, the actual physical objects in their actual current locations, are no longer reachable. The expansion has carried them too far. Anything we could send toward them would never arrive. The light from them right now, at this moment, is heading toward Earth, but it will not reach us. We will see the light from 1 billion years ago. We will never see the light from now. The disconnect between sight and reach is total. We're looking at corpses, beautiful, glowing, complex corpses, lit by ancient light. The current reality of those galaxies is hidden from us forever. There's another way to think about this. Imagine you have a friend who lives very far away. You used to talk to them by sending letters. The letters take a long time to arrive, but they always do. You can hold a conversation, even if it's slow. Now imagine that the post office stops delivering. The letters keep being sent, but they're being slowed down. They're being lost in transit. Eventually, no letters arrive at all. You can still write to your friend. You can still receive their old letters that were already in the mail before the breakdown, but no new mail can pass between you. Your relationship is suspended in amber, frozen at whatever moment the connection broke. That's what's happening between us and most of the universe. The connection is breaking slowly, irreversibly. The light still in transit will arrive, but after that, nothing. The galaxies. And we are sealed off from each other, even as we can still see what they were. Even within our reachable bubble, there are reminders of how strange and isolated cosmic objects can be. The Boomerang Nebula, about 5,000 light-years away in the constellation Centaurus, is the coldest known natural object in the universe. Its temperature is just 1 degree above absolute zero. It's colder than the cosmic microwave background, which is the leftover radiation from the Big Bang and serves as a kind of universal thermal floor. The Boomerang Nebula is colder than the universe itself, on average. The gas there is expanding so rapidly from the dying star at its center that the expansion is cooling the gas faster than it can warm itself by absorbing background radiation. It's a small pocket of darker, colder space than anywhere else we know. Imagine being in that nebula. The cold isn't just metaphorical, it's real. It's the absence of motion. The atoms there are barely moving. The space is silent in a way no other place is silent. And it's 5,000 light-years away, completely beyond reach, observable only through telescopes that detect its faint emission across the void. There are other strange, isolated cosmic objects. Brown dwarfs, failed stars too small to ignite hydrogen fusion, drifting through interstellar space alone, slowly cooling over billions of years. Rogue planets, worlds without stars, ejected from their solar systems long ago, wandering through the dark forever. There may be more rogue planets in our galaxy than there are stars. Each one, a frozen, lightless world, drifting through the void, never approaching another body, never warming up, never being seen. Imagine being on a rogue planet. The sky has no sun. The temperature is just a few degrees above absolute zero. There might be liquid water if there's enough internal heat from the planet's core, but the surface is dark. There are no seasons, no day and night, just permanent cold and permanent darkness. Stars in the distant sky, too far to provide warmth. The whole planet drifting through the void at a few kilometers per second, going nowhere, encountering nothing. There are creatures, possibly, on rogue planets. We don't know. The galaxy might be full of them. Frozen worlds with bacteria or simple life forms thriving in subsurface oceans, never to make contact with anything else, never to even know that other planets exist. The universe is full of isolated objects, each one running its own slow, lonely physics. The wall isn't just between galaxies. The wall is everywhere, between stars, between planets, between any two things in the cosmos. The default state of the universe is isolation. Connection is the rare exception. That's the cosmic wall. That's the deepest layer of cosmic distance. Not just that things are far away. Not just that things are far away in time as well as space, but that things are far away in a way that's actively getting more far away, and there's nothing we can do about it. The wall isn't built. It's growing. It's coming for us, slowly, inevitably, forever. The reachable universe is a small island in an infinite sea, and the island is shrinking. The galaxies that exist tonight, somewhere in the visible sky, may already be unreachable. If there are civilizations in those galaxies, civilizations like ours, looking up at their own night sky, they're seeing the same thing. We're all trapped in expanding bubbles of reachable space, each bubble shrinking, each one isolated from the others. The universe is full of people, perhaps. All of them unable to find each other. All of them watching the same slow loss of cosmic visibility. And even within the reachable bubble, the situation isn't great. The local group, the gravitationally bound region containing the Milky Way and Andromeda and the dwarf galaxies, will eventually merge into a single elliptical galaxy. Once that happens, the merged galaxy will sit alone. The expansion will have carried everything else beyond reach. Whatever beings exist then will live in a single galaxy, in a sky that contains only one galaxy. They won't be able to see other galaxies. They won't know the universe is anything more than what they can see. The future is a single galaxy in an infinite, dark, empty space. Let me describe what that future will actually look like for any beings who exist in it. Imagine 100 billion years from now. The Milky Way and Andromeda have completed their merger. The new combined galaxy is a vast elliptical, no longer with spiral arms, just a smooth distribution of stars. The night sky from any planet in this galaxy is full of stars, but the stars are mostly older now. The bright blue stars of our era, the ones that burn fast and die young, are mostly gone. What remain are the smaller, dimmer, longer-lived stars, the red dwarfs and white dwarfs, and slowly fading remnants of larger stars. The galaxy is darker than ours, redder, quieter. Beyond this galaxy, the sky is dark, empty. There are no other galaxies visible. The expansion has carried them all beyond detection. The cosmic microwave background, the afterglow of the Big Bang, has redshifted so far that it can no longer be detected. There is no evidence of an expanding universe. There is no evidence of a Big Bang. There is no evidence of anything outside the local galaxy. Astronomers in this future, if any exist, will look at their sky and see what looks like a complete universe. A single galaxy surrounded by emptiness. They might assume the galaxy has always been there, alone. They might develop cosmological theories that make sense only of what they can see. They might decide the universe is small, finite, and unchanging. They will have no way to know about the rest. The evidence will be gone. Even the stars in their galaxy will have changed. The structure of the merged Milkomeda will have settled into a smooth elliptical shape with no spiral arms, no obvious organization. New stars will still form, but more slowly, because the gas reserves will be depleting. Eventually, in 1 trillion years or so, star formation will essentially cease. The galaxy will be filled with stellar remnants, white dwarfs cooling slowly toward black, neutron stars, black holes. The light will dim. The galaxy will become a dark place, lit only by the faint glow of dying stars. That's the deep future of our local region. A single galaxy slowly fading, surrounded by infinite emptiness, and we won't be there to see it. Humans, even if we survive that long, will be unrecognizable. The sun will be dead. Earth will be gone, possibly engulfed by the sun's red giant phase about 5 billion years from now. Whatever beings exist on whatever planets exist in the merged galaxy will not be us. We are creatures of this specific moment in cosmic time, with this specific configuration of stars and galaxies and observable universe. Our descendants, if any, will live in a different cosmos, with different rules, different visible structures, different possibilities. We are seeing the universe in a kind of golden age. There is enough cosmic history visible to figure out what it all is. There is enough light still arriving to learn from. There are enough other galaxies still detectable to study. None of these things will be true forever. The window is closing. If you wanted to plan an interstellar civilization, the best time to do it would be earlier, not later. The future has fewer options. Less can be reached, less can be learned. As the cosmic horizon shrinks, possibilities collapse. The deep future is a smaller universe. Even if it lasts longer, we're at a high point, a peak of cosmic accessibility. From here, things only get more isolated. That's the terrifying reality of cosmic distance. Not that things are far away, not that we'd need huge ships to reach them, not even that we don't have the technology. The terrifying reality is that the distances are growing, the wall is closing, and most of the universe was already too far away the moment we were born. So, why do we keep looking? Why do we still build telescopes, send probes, listen for signals, measure expansion? Why do we keep trying when the wall is real and the journey is impossible? I think the answer is that the looking itself is the point. We are conscious beings on a small planet, in a small galaxy, in a small corner of the cosmos. We have brief lives. We will never reach Proxima Centauri, let alone Andromeda, let alone the cosmic horizon. Most of what we can see, we will never visit. Most of what exists, we cannot even see. But we look anyway. We look, and in looking, we know. We learn, we measure, we build models in our minds of a universe we'll never touch. We figure out the size and age and structure of a cosmos that is almost entirely beyond our reach. The Voyager spacecraft, drifting silently into the dark, carrying golden records that no one will probably ever play, is a kind of gesture, a message in a bottle thrown into an infinite ocean. The message itself isn't really for the alien who might find it. The message is for us. It's a way of saying, we existed. We were here. We tried. Curiosity is defiance against the wall. Knowing that we can't reach Andromeda doesn't stop us from wanting to know what Andromeda is. Knowing that we can't talk to a civilization 50 light years away doesn't stop us from listening, in case one is there. Knowing that most of the visible cosmos is already past the horizon doesn't stop us from looking at the small fraction we can still reach, marveling at what's there, mapping what we can. The wall stands between us and the rest. But the looking is what we do anyway. Think about the history of human curiosity about the cosmos. For most of our existence, we had no idea how big the universe was. We thought the stars were lights painted on a sphere just above the atmosphere. We thought the Earth was the center of everything. We told ourselves stories about the lights in the sky, made them into gods and heroes, gave them names and personalities. Every culture had its constellations, its myths, its explanations. None of those explanations were correct in any modern sense, but the looking was real. The wonder was real. The desire to understand was always there. Then, slowly, we figured it out. We built telescopes, we measured parallax, we computed distances. We discovered that those points of light were suns, like ours, but unimaginably far away. We found galaxies. We mapped the cosmic web. We measured the expansion of the universe. We figured out the Big Bang. We learned piece by piece what we are and where we are. Each new discovery made us smaller. The universe kept expanding around us in our understanding. The Earth was no longer the center. The Sun was just one star among billions in our galaxy. The galaxy was just one of trillions. We are not even the only large galaxy in our local group. Andromeda is bigger than us. We're not central, we're not special, we're just here. But we know that we're here. That's the thing. We know it. Most of the universe doesn't know anything. It's gas and dust and stars and planets and dark matter, all running according to physics, none of it aware. We are, as far as we know, the only things in our local region of the cosmos that are aware of being there. The only things asking questions, the only things looking up. That awareness is precious. It's small, brief, fragile, and maybe unique. The universe has been around for nearly 14 billion years. For most of that time, there was no awareness anywhere we know of. The first 100 million years, no stars yet, just hydrogen and helium expanding in dark space. The first billion years, stars but no planets. Then planets, but no life. Then life, but only single cells. Eventually, after billions of years of evolution, brains. Eventually, after even more time, brains complex enough to look at the stars and ask what they are. That's us. That's what we are. The universe, after a very long time, growing the equipment to wonder about itself. And consider how much had to go right for us to be here. The Big Bang had to produce just the right amount of matter with just the right initial conditions for galaxies to form. The first stars had to live and die, forging heavy elements in their cores and spreading them across space when they exploded. Those heavy elements had to gather into clouds that collapsed to form new stars and planets. Earth had to form in the right place, far enough from the sun for liquid water, but close enough for warmth. The right collisions had to happen to give Earth its moon, which stabilizes our climate. Asteroids and comets had to deliver water. Life had to emerge. Oxygen had to accumulate. Mass extinctions had to happen at the right times to clear the way for new evolutionary radiations. Mammals had to evolve. Primates had to evolve. Our specific lineage had to make it through all the bottlenecks. Each of us, individually, had to be born from a specific combination of ancestors going back generations. The chain of contingent events leading to your existence is so unlikely that, looked at one way, you almost certainly shouldn't be here. The universe didn't have to make you. Most universes, if there were others, probably wouldn't have. You are the result of 14 billion years of cosmic chance. You are an extraordinarily unlikely thing. And yet you are here, looking at the stars, wondering about distance. There is also something to be said for what's reachable. The unreachable parts of the cosmos are vast, but the reachable parts are also vast. Even within our local group, there are dozens of galaxies, hundreds of billions of stars, perhaps trillions of planets. Even if we never leave the Milky Way, there's enough to explore here for billions of years. Even within our solar system, there are 8 planets, many moons, asteroids, comets, places we've barely begun to study. Even on Earth, there are oceans we haven't fully mapped, species we haven't discovered, places no human has ever stood. The wall keeps us inside a bubble, but the bubble is enormous. The bubble contains everything that has ever mattered to a human being. Every person you've ever loved is inside the bubble. Every piece of music you've ever heard, every book you've ever read, every meal you've ever eaten, every moment of your life, all of it happens inside the bubble. The wall doesn't take any of that away. It just reminds you that the rest is, in a real sense, gone. That the universe outside the reachable bubble is a place of eternal silence, of unanswered questions, of beauty no one will ever witness up close. You can hold both things at once: the terror of the wall and the beauty of what's inside it. The bleakness of being unable to reach most of what exists, and the wonder of being able to see any of it at all. We are the ones who got to know. That's what cosmologists sometimes say. In the deep future, no civilization will be able to look up and learn about the universe the way we can today. The expansion will have erased the evidence. We are here, in this moment, when there is enough evidence to figure out what the universe is. That's a privilege, a small one, granted to a small species on a small planet, but a privilege nonetheless. Think about what it means to be a witness in cosmic time. The universe has gone through eras of unimaginable change. The era of inflation, when space itself stretched faster than light for a fraction of a second after the Big Bang. The era of nucleosynthesis, when the first atomic nuclei formed in the cooling soup of particles. The era of recombination, when atoms could finally hold onto their electrons and the universe became transparent. The era of the Dark Ages, when there were no stars, just hydrogen and helium drifting in the dark. The era of reionization, when the first stars lit up and ionized the surrounding gas. The era of galaxy formation, when stars clumped together into the structures we see today. The era of stelliferous burn, the era we live in, when stars are forming and dying everywhere we look. After our era will come the degenerate era, when star formation has ceased and only stellar remnants remain. Then the black hole era, when even the remnants have decayed and only black holes remain, slowly evaporating through Hawking radiation over time, scales that dwarf the current age of the universe. Then the dark era, when even the black holes are gone, and the universe is just a thin gas of photons and elementary particles spreading out into an expanding void. We are alive during the most active, most luminous, most diverse era the universe will ever have. After us, things only get quieter. The stars slowly burn out. The structures slowly fade. The universe slowly winds down toward thermal equilibrium and silence. You are the universe knowing itself. That's not a metaphor. The atoms in your body were forged in stars that died billions of years ago. You are made of stardust, recycled, and rearranged. You are matter that has organized itself enough to look back at the matter it came from and ask what it is. You are an observer in a universe that, for the most part, has no observers. The rocks don't notice. The gas clouds don't care. The galaxies don't ask questions. You do. That's not nothing. In a universe defined by silence and eternal isolation, you are a brief, small, miraculous moment of awareness. The distances are immense. The cosmic horizon is closing. None of that takes away the fact that you, here, tonight, are looking up at the sky and wondering. There's a kind of beauty in that. Not the beauty of triumph, because we're not winning. The wall is going to keep closing. The expansion is going to keep accelerating. The galaxies are going to keep slipping away. We can't stop it. But we can witness it, we can document it, we can know about it, and in some small way, that's enough. Imagine what it would be like to live in a universe where there was no wall, where everything was reachable, where you could send a message to any galaxy and get a reply within your lifetime. where civilizations across the cosmos talked freely, shared knowledge, traded culture, where the night sky was full of voices. That isn't our universe. Our universe is silent, with walls, with distances that compound against us. But maybe the silence is part of what makes the looking valuable. If everything were easily reachable, would we still look up with the same wonder? Would the night sky still feel mysterious? Would the questions still feel deep? Probably not. The wall is part of what makes the universe feel vast. The unreachability is part of what makes it feel real. If we could just hop over to Andromeda for the weekend, Andromeda wouldn't seem so awe-inspiring. The fact that we can never go there, that the light from there is older than our species, that we will only ever know it as a faint smudge in the sky, makes it more important, not less. The wall amplifies the wonder. The universe will continue, long after you're gone, long after the human species is gone, long after the sun has died and the Milky Way has merged with Andromeda and the cosmic horizon has shrunk to almost nothing. The universe will keep doing whatever it does. It will not remember us. It cannot remember anything. It just continues. But for this moment, you exist inside it. You can look, you can know, you can think about the wall and the distances and the unreachability of most of everything. And even that thinking is something the universe is doing through you for the brief time you're here. The wall is real. But so is the fact that you're still here, staring at it. That might be the most terrifying and the most hopeful thing of all. Look at the people in your life tonight. The ones close enough to touch. The ones you can call without a delay. The ones whose voices reach you in real time. That kind of closeness is rare in the universe. Most of the cosmos is too far away for connection. Most of what exists, no one will ever talk to. But the people in your life, the ones nearby, are reachable. You can hold them. You can hear them respond to you. That's worth something. In a universe that mostly says nothing back, the small bubble of reachable connection around you is a kind of miracle. The walls of the cosmos are vast, but the room you actually live in is small enough to be known. The people in it are close enough to touch. The world outside your window is reachable on foot. The continent you live on is reachable in hours. The Earth is reachable in a day. The Moon is reachable in 3 days. Mars is reachable in months. Past Mars, the reachability drops off sharply. But within your immediate sphere, everything is connected. Everything is reachable. Everything is here. So when you look up at the stars tonight, knowing what you know now, knowing that most of them are time capsules and most of the universe is beyond reach and the wall is closing, look down again. Look at what's near. Look at what's reachable. Look at the small, finite, beautiful island where everything you care about happens. The wall holds you in, but it also gives you the room to live. There's a phrase that astronomers sometimes use when they talk about the universe. The Drake equation. It's a way of estimating how many intelligent civilizations might exist in our galaxy, given various assumptions about the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, and so on. The equation gives different answers depending on what numbers you put in. Some answers suggest the galaxy is teeming with life. Other answers suggest we're alone. Frank Drake came up with the equation in 1961 as a way of organizing the discussion at a meeting of scientists interested in the search for extraterrestrial intelligence. The equation isn't really designed to give a definitive answer. It's designed to help us think about the question, to break the problem down into smaller pieces, each of which we might eventually be able to estimate. The first piece is the rate of star formation in our galaxy. We have a reasonable handle on this. About 1 to 3 new stars form in the Milky Way every year, on average, over its history. Multiply that by the age of the galaxy and you get hundreds of billions of stars total. The next piece is what fraction of those stars have planets. Until the 1990s, we didn't know if any other stars had planets at all. Now we know that planets are extremely common. Most stars have planets, maybe almost all of them do. So that fraction is close to 1. The next piece is what fraction of those planets are in the habitable zone, where liquid water could exist. This depends a lot on what kind of star it is. For sun-like stars, it might be a few percent. For red dwarfs, it could be higher in some senses, but lower in others, given the radiation flares. The next piece is what fraction of habitable planets actually develop life. This we don't know at all. Earth developed life relatively quickly after it cooled. Maybe life is easy. Maybe it happens almost everywhere conditions allow. Or maybe Earth was extraordinarily lucky and life is extremely rare. The next piece is what fraction of life-bearing planets develop intelligence. Again, we don't know. Intelligence on Earth took billions of years to emerge, and it almost didn't. There were several mass extinctions that nearly wiped everything out. Maybe intelligence is the rare step. Maybe most planets have life forever, but never anything that builds telescopes and asks questions. The next piece is what fraction of intelligent civilizations develop technology capable of communicating across stars. We've done it. We've sent signals. So at least one civilization has reached this stage, but we don't know how common it is. The last piece is the lifespan of communicating civilizations. How long do they exist before they stop transmitting, either because they've gone extinct or because they've moved on to other forms of communication that we don't know about? This is maybe the most important factor. If civilizations only broadcast for a few hundred years before stopping, the chance of overlap with another civilization is very small. Multiply all these factors together and you get an estimate. Different scientists put different numbers in and get answers ranging from millions of civilizations to fractions of one. The honest answer is that we don't know. We don't have enough data. We've only really searched for alien signals for a few decades, with limited equipment in a tiny fraction of the sky at a few specific frequencies. We could be missing them entirely. They could be there, broadcasting, just not in ways we've thought to look. Or they could not be there at all. We can't tell. But the Drake equation is a way of asking the question, of saying, maybe we're not alone. Maybe somewhere in this galaxy there's another civilization, looking up at their own stars, wondering the same things we wonder. Maybe there are millions of them. Maybe there's just one or two. Maybe there are none, and we're it. Whatever the answer, the wall stands between us. Even if there are millions of civilizations in our galaxy, we'd never meet most of them. The distances are too vast. The times are too long. The communication is too slow. We could be living in a galaxy crowded with intelligent life and never know, because none of them are close enough to talk to. That's the loneliness of cosmic distance. Not just that we might be alone, but that even if we're not, we're still effectively alone. The cosmos doesn't allow for community at galactic scales. And consider the time scales. Modern humans have existed for about 300,000 years. Civilization, in the form of agriculture and cities, for about 10,000 years. Industrial civilization for 200 years. Radio technology for about a century. We've been technologically capable of detecting aliens for less than 100 years. The Milky Way is 13 billion years old. There has been time for civilizations to rise and fall many times over. Hundreds of times. thousands of times maybe, each one lasting a few thousand years, then disappearing. The vast majority of civilizations that have ever existed in our galaxy, if there have been any, are gone. Their stars still shine, their planets still orbit. But the civilizations themselves have ended. We're looking at corpses, beautiful, distant corpses, all of which we'll never reach, even if we wanted to mourn them. The galaxy is a graveyard, possibly, with us as the only currently active mourners. And yet, the very fact that we wonder about it, the very fact that we ask, is the universe's way of trying to know itself. Every signal we send, every probe we launch, every telescope we build is the cosmos reaching for connection through us. Maybe that connection never comes. Maybe nothing ever answers back. But the reaching is part of what we are. So we look. We send our messages out into the dark. We listen for whatever might be listening back. The cosmos doesn't owe us a reply, but we keep asking anyway. Good night. Sleep well. Out there, beyond the wall, the universe is doing its slow, indifferent thing. In here, inside the reachable bubble, you have everything you need. The stars are old. Their light is ancient. But you're here now, and that's the only present moment any of us ever get. Think about how rare this is. Across the entire history of the universe, across all the billions of years and all the trillions of stars and all the unknowable vastness, there is only one moment when you exist. Tonight is part of that moment. The sky above you is part of that moment. The dim glow of distant stars. The faint smudge of Andromeda, if you can see it. The inky black between the points of light. All of it is yours, briefly, for the time you're here. The universe has been mostly empty of awareness for almost all of its existence. The early universe had no observers. The Dark Ages had no observers. The first billion years of stars and galaxies had no observers, anywhere we know of. Even now, in our era of cosmic luminosity, observers are probably extremely rare. Most planets don't have life. Most life never becomes intelligent. Most intelligent species don't last long enough to think about cosmic distances. You are an observer. You're doing observing right now, listening to this voice, thinking about light years and Voyagers and walls and bubbles. The cosmos is being witnessed through you. The act of witnessing is happening, for a little while, in this small bubble of awareness around your consciousness. After you stop watching, after you go to sleep tonight, the witnessing continues elsewhere. Other people are looking up at their own skies. Other minds are wondering about their own questions. Tomorrow, the witnessing continues. Next year, next century, until eventually our species ends, and the witnessing stops being us, and either passes to whatever comes next or fades out entirely. But for now, it's us. For now, it's you. The wall is real, the night is long, the cosmos is mostly silent, but the bubble is enough. Sleep well, traveler. The light is old, the distances are vast. The future is closing in. None of it can take away this moment, here, in your small, reachable bubble where you are alive and aware and thinking about it all. That's enough. Good night.